Hey, thank you so much for attending this session. Very excited to talk to you about what we're doing at E6 Data. And I think the most exciting part of it is that virtually everything that we're doing is being built like about 1 kilometer away from here on Infantry Road. Excited that some of the folks who are actually building this are in the room and can learn from your questions and feedback. So we've sort of gone through a very rich sort of exploration of the data lake, data lakehouse, data warehouse, sort of trade off some of the questions around why and how and the journey to the lakehouse. But this is all to serve an end goal, right? Like business, like this is to advance certain business ends, to serve customers better, to deliver on certain end goals, whether it's to get new business, prevent fraud, to cut costs, and so on. So, and this is sort of, we come in at the other end of the spectrum. Once you have taken the trouble to set up a lakehouse, how does that get used? What do your business users see? And that sort of a thing. So let me quickly get started. I think it's fair to say, just based on today, that lakehouses are the new center of data gravity, right? And the reason for this is that it serves as that one single unified platform for both your traditional analytics as well as your more modern AI use cases. And what are these use cases? It could fill up like a slide that's 10 times as large, right? It could fall under different buckets, whether it's infrastructure and security or good old analytics, whether it's batch or whether it's ad hoc or scheduled, and the lakehouses that you build will serve all of these needs, right? So hence the importance in that single sort of platform, and obviously, like a lot of the pain that you'll take to build these lakehouses serves all of these different needs, right? So it's well worth it. Now, so these are, let's say, these downstream data consumers, whether they're humans or downstream apps, and essentially you're trying to connect some sources to the destinations, right? Like people that use the data. So you get data into some location, let's say in its raw form or directly into Parquet form. You use different engines to, get it into maybe a more performant file format and table format, which now starts resembling a lakehouse, right? Like you have like either iceberg tables or hoodie tables or delta tables, and you may take this through multiple stages of modeling or just a few stages of transformation before this data is sort of ready for consumption. So mirroring very quickly what Ankur said in his last session, like from here, you have, let's take the example that Ankur gave. You have you have hoodie tables, and you have it across granular as well as summarized data. And you might then query it using a data warehouse, right? Like, or you might sync it into a data warehouse. So that's one architecture that you see, right? So take the transform data, load it into Snowflake or BigQuery or Redshift. Of course, a new pattern has emerged where Snowflake or BigQuery can also allow you to query external hoodie tables, but that's a sort of a special case for them. Another thing that's emerged is that, hey, as query engines have gotten better on the lakehouse, you now can have query engines that you sort of spin up within your own cloud environment, so you don't need to move the data from your S3. And you can either query granular data or summarize or aggregate data. Right? So both of these are now possible. And in this sort of weird, wonderful, brave new world of the lakehouse, you can have horses for courses, right? You pick your engine for your use case, and it does a job for you. So you can use Athena for something, good old Spark for something else, or Trino for something else, or Databricks' new sort of Photon engine for like latency-sensitive queries, let's say, right? And there are certain use cases that need either I'll use a jargon around real time, but either you need ingestion latency to be super low or query latency to be super low. So you may have a new class of engine, which you call a real-time engine, and you may either stream data directly into it or via S3, like all combinations are possible. Right, so now what's your ideal state? Having taken all the trouble to sort of build this data lake, you want to serve as many use cases as you can from that one place. Right, so there may be different engines that are out there, new ones emerging all the time. And your first question is, do I need to do anything more, right? Like I've taken the trouble to get this lakehouse infrastructure in place. Is there any further data movement? Is there any further pre-computation or like intermediate stages of processing before I can get to my business users' needs, right? Or my data products' needs. And those needs are specific to individual use cases, right? Some could be around latency, around how many queries you need to support a second, an hour. It could be around cost, like let's say you have large reconciliation use cases where like it's just very cost sensitive. How granular of data access do you need? How many dimensions? Do queries stay the same? Do they change all the time? So all of these influence the choice of engine. But essentially your ideal state is like, I would love to do everything from this one lakehouse, having taken the trouble to actually build it. Right, so this is the ideal state, but remember we started on that second slide with use cases. The challenge is that not all use cases are alike, right? Like you all know that within your own organizations, you'll have probably few dozens of different use cases. Right, sticking with the lake and the water-based analogies, some use cases are like this, right? So it's not super mission critical. No one cares if it takes like 30 seconds or 2 minutes. No one, like it's purely, it's fairly tolerant and chill. But some use cases are like this, right? It's production. It's carrying a heavy load. It's like either internal facing to certain very critical downstream apps or certain very influential decision makers like executives, let's say, or it's feeding downstream data products and automations, right? So it's a world of difference from this, right? But they're both served off the same lakehouse. So our submission is that this, I don't know what to call it, so I just call it the top 10%, but what I refer to is this class of use case. This we feel is currently underserved by the query engines that exist, right? Like, and I say that with the greatest of humility because we are like huge fans and students of everything that has sort of come in the past. We've learned from it. We're like, even today we're inspired in terms of new ideas and these things of existing sort of engines, both commercial as well as open source. But our belief is that as you see more and more use cases coming on top of data lakehouses and software engineering thinking and architecting sort of thinking coming into data products, you're now designing for certain guarantees. You're designing for certain requests per second, right? Like, except that these are now analytical data products. There's an engine behind the scenes that has to support these, right? You have complex computations because nobody does like hundreds of stages of intermediate modeling or transformation. The complexity is often in the query, right? Like, so we often see 2,500 line queries that have to execute in 1-2 seconds, right? So complex queries. And it's not just on the most recent data. It could be on historical plus recent data. And this could change all the time, right? So other complexities that we see relating to the infrastructure is that it's no longer that the base load is like 80, peak load is 100, right? There can be a very drastic variation between base and peak load, and you still need to maintain guarantees and, like all of the stuff across these, right? So, and these tend to be massive clusters, right? So on top of all this, you find that some of these top use cases end up contributing disproportionately to your costs. So some of these individual use cases cost you this much, either in compute if you're purely using open source, or license costs if you're using commercial software, right? And we all know that costs are suddenly super heavily scrutinized. It's almost that most teams today, like, when data vendors talk to data teams or to CDOs, like, you're first asked about cost, not about what new functionality are you bringing in or what new performance are you bringing in, right? And this is sort of like a devil and the deep sea choice, right? Like, you all live and breathe this trade-off every day. So the cloud eases some things, but it's essentially this, right? There's no free lunch is the belief that's out there because everyone knows how this sort of trade-off sort of works. And like a VC was here earlier, so I added this slide on the fly while he was presenting, just to since there was so much interest around the business side of things. $1 million that you save to the bottom line, based on the price to earning multiple of a company, translates to $20 to $100 million, depending on the PE ratio of your company. So you see now why people are so cost obsessed. Right, so I think like one thing as the field is maturing is that data leaders are getting increasingly business savvy and learning how their work translates to business outcomes, whether it's a revenue generating use case or something that directly increases shareholder value. Right, so with that I'll introduce what we do. Right, like, so we're a brand new Lakehouse native distributed query engine. specifically around those top, like painful, heavy-duty sort of use cases. And like our product is basically efficiency, right? We're a much leaner, much more efficient engine. What that translates to in workloads or data products that you build is especially in these high throughput, complex queries, low latency scenarios, we see P95 latencies improving by 10x or greater, or your costs just dramatically plummeting, right? Like 60% lower all-in costs, while maintaining the simplicity and the sort of architectural elegance of your lakehouse. We have no business dictating which lakehouse format you should be on. You could be on Hudi today, Iceberg tomorrow, right? You could be on commercial Delta versus open source Delta. So we will just plug into anything. And the idea, or at least the aspirational experience that we're building towards, is that there should be no changes at your application layer whatsoever. It's just an infrastructure change and something that comes in there. So if your existing lakehouse is like this, with E6 data, it would just be that you pick which use case where this would benefit you, and you spin it up in parallel, run for a few weeks, A versus B, run the same workload on the same data and the same query, and you're like, okay, listen, I'm getting what I need, so let me migrate that one workload onto E6 data. But your users, it's completely transparent to your end users and your data consumers. Right, so that's the sort of product strategy that we follow, that we try to deliver on in terms of the end experience. So I have a couple of example use cases here, so I'll come to this when we go to these things. But I'll stop there because obviously the question is that we're all engineers. We all are aware of whether it's Snowflake, Databricks, BigQuery, or whether it's Trino, Spark. Really, it's like, how do you do a 10x better performance? Right, so this is what the next section sort of covers. Let me quickly check how much time we have left. So yeah, so let me stop here. So the next section is really how we do this, like what's under the hood. And like our real belief is that if you think of Snowflake, or if you think of Trino even as an open source project, as a skyscraper, right? Like we feel that you can't innovate at the top, the 200th story of a skyscraper and really deliver 10x, right? Like you really have to rewrite the foundations, which means starting from scratch, right? You can't do it any other way. So if we looked at what architectural challenges we felt that Spark and Trino or Presto had for these like particularly demanding use cases, right? Like, so this is not something that applies to the general use case. This is for those power user use cases, if you will, or those top 10% of use cases. So whether it's the driver in Spark or the coordinator in Trino or Presto, and BigQuery largely has an analogous architecture internally. So the constructs are the same, right? You have one sort of brain, and then you have executors or workers, and you either operate on smallest units of data like RDDs or splits. Like constructs are very, very sort of applicable in both cases. But our first observation was that, hey, listen, this top level entity is just doing way too much, right? Like 7, 8 different jobs or tasks, right? From parsing to logical planning, physical planning, to the actual sort of distributed execution, scheduling, and coordination, and all of that stuff, right? And our worry was that, listen, this is all just for one query, right? So what if that query is particularly large, particularly complex, or has certain characteristics? What happens then, right? Like, because everything is happening in one physical machine. And specifically around that point in red, because all context around how tasks are distributed and scheduled are done in that box, it can't scale out, right? So it becomes a single point of failure or acute performance bottleneck for these higher end use cases that data products typically see, right? So that was one issue that we really saw. And this is all just for one query, remember. There could be hundreds of queries coming in at a time, right? You can't predict sometimes. So the other thing that we found was that the nature of the approach that they take to distributed execution is to essentially decide what task has to run on which physical resource before the start of execution of that stage or of the query in let's say, Presto's case, right? What we felt that this would, like the issue that we felt this would cause was that if you have a particularly latency sensitive query, let's say it has to run in 3 seconds, but there's an undue load on the system and it looks like it's going to run in 20 seconds, You could scale out, right? Like executors can scale out, they're stateless. But a lot of the times it takes 240 seconds or so for a new node to come on stream. So what happens if you're getting dozens of queries per second in that interim period, number one. But more worryingly, any new scale out resources will only benefit new queries, not the in-progress jobs, right? So that's because there's a static upfront mapping of what runs where before the commencement of a query, let's say in the case of Trino. So this again we felt was if you're in that top 10% of use cases where you need to guarantee an SLA around response time, this is a challenge. Right, so our view was to say that, okay, if there are 8 jobs to be done, as an example, you should have 8 lightweight components. We were, we're born, we're a young company, so we were able to say, hey, let's make the entire engine Kubernetes native itself so that there's no tight mapping between a logical construct and a physical machine, right? Like, so those types of things. So what this allows us to do is say, if you make this completely disaggregated, each of these can be something that responds to a load trigger. So you can granularly and independently scale each of these internally, and they can learn over time, right? So what this means is that now each component can scale out depending on the load that it sees. The other, like I said, in contrast to the upfront or static distribution model of Spark or Trino, we built something that's completely on the fly, a dynamic distribution model, right? So if you're halfway through a query and a new node comes into the cluster or a new pod comes into the cluster in our construct, that can benefit your in-progress job also, not just future jobs, right? And being Kubernetes native, if you pre-provision, enterprises, you're not really constrained on the raw node cost. These pods can spin up in like 1-2 seconds, and it's not like a full VM having to spin up and waiting for such a long time. So what this also allows us to do is take the decision of like what task runs where or what set of tasks run where as late as possible and based on the most updated view of the system load. Right, so in cricket we say, right, like try and play as late as possible to avoid like edging or whatever. So this is the equivalent of this. So the best analogy that I give is imagine we're taking a Bangalore to Delhi road trip. And Google Maps, imagine if Google Maps could not reroute you depending on traffic, road closures, or that sort of stuff. Because the plan is decided upfront, no changes. We felt that that's super risky, especially in high concurrency, high complexity, high scale scenarios. Right, so this approach leaves, like you don't have to like mastermind that decision upfront and figure out like everything upfront. Just do it on the fly. Right, so obviously all of this meant that we could not touch a line of what was available in open source and just fork it. We had to build completely from scratch, right? But like we're fortunate that like some of the extraordinary people who are in this room were up to the challenge and like could think this up, and help us build this. So other benefits, of course, are that it's massively performant, it's scalable, it can scale, like it scales linearly. The same latency that you achieve at 1 QPS, you can achieve at 100, 200 because of this architecture, and there's no single point of failure. Other things that we did, which again, like there's some amazing literature out there that teaches you like, different approaches to building. And we noticed that, quite early, this would be a very big decision. How does data flow from one operator to the next? And we noticed that except for Snowflake, hats off to them for like having thought of this like a decade plus ago, all other distributed engines were essentially pull-based or the volcano-based model where the top level operator will trigger lower level operators and so on and so on and so on, all the way down to the table scan task. But this would sort of couple the consumption of data from the processing or reading of data. And when you have extremely parallel distributed execution, the coordination overheads and synchronization overheads would just like eat away a lot of potential performance gains from things that you do like vectorization and all that. Because vectorization is within one operator. But this is how data flows across or between operators. Right? So these were those foundations of the skyscraper that we felt we should build that can actually give us the lion's share of performance gains. So there are like many more details, but this is an interesting talk, by the way. There's a CMU database systems lab talk that the DuckDB team presented on how they started with a pull-based model, realized that, holy, I think we're going to face problems. Let's go and implement the push-based model. And it's a really interesting talk. They're, of course, not a distributed compute engine, but the talk is very relevant nonetheless. So I'll stop there and can we're growing fast. We're building like the nerve center of this just a couple of roads down. So we're like growing fast. So if this is something that excites you and you're interested in contributing to the journey, we'd love to talk to you. But I'll pause there and check for any questions.